Welcome back to this session. In this session, we will continue from where we left off last session. So, if I summarize what we have studied last session, we have come across what is load, what are the different kinds of load that we need to consider when we design any structure, then the effects of load on a member, then mechanical properties, classifications of materials. So all these things are covered. Today's topic is stress. It is stress. And now what stress means? Stress is a physical quantity, and it defines force per unit area of the material. If I say force per unit area of a material, to simply make you understand, say that I have one member here, let this be one member, and I'm applying a force here, force P. Alright, now I want to find how much stress is being produced in this body after I apply a force. So this stress is signified by a symbol sigma, and stress will be equal to force that I'm applying divided by its area. So the area will be area of this cross section. So area A of this cross section. So my simply stress is a physical quantity, and it defines force per unit area applied to the material. Force per unit area applied to this material. So this is my stress, and it is already given here. As you can see, stress is equals to force by area. So stress is defined as a physical quantity that defines applied force per unit area of the cross section of that material. I hope it is clear. And its SI unit is equal to Newton per mm square, or if it is equals to 1 MPa, it will be equal to 1 kilonewton per mm square. So next we have types of stresses. So these are the different types of stresses. So we have direct stress and normal stress. Then you have shear stress, bending stress. So under this direct and normal stress, we have tensile stress and compressive stress. Just as different types of loads, and under different type of load, there was direct load and or axial load. So under direct load and axial load, there was tensile load and compressive load. So similarly here, that direct load will the direct load of concept was something like this, right? We have a material here, and it has its axis, and if I apply a load from this axis here, force P, let us say, so whatever stress is produced after applying this force P here, that stress that is produced will be either tensile stress or it will be either compressive stress. So let us go further. I'll explain you one by one. So here, direct stress or normal stress, right? So in this direct stress or normal stress, we have stresses which acts normal to the plane on which the force acts axially. So it means I have a body here. So in this body, the direct load will be acting first. Direct load will be acting directly on its axis, right? Force P. And now the stress generated due to this applied force, which is applied directly in the axis of this member, will produce a stress which will be force by area of this section. So this is known as direct or normal stress. And if we come to tensile stress, now I have a body again, right? Its axis is running from here. If the force is applied if the force is applied in this direction, opposite to each other, and applied directly in its axis, through its axis, P and P. So the stresses so produced in this area of this body will be tensile stresses, because this body is under tension. Now next we have compression. For compression, it is again the same concept. I have a body here, right, and its axis, and now if the force is applied in this direction, inside, if the forces are applied inside the body, force P, and the stress is produced in this body. Now this body here is under compression. It is under compression because the forces are applied inward, right, and the body is under compression. Now the stresses produced in this body will be force by area of this section, and the stress so produced here will be compressive stress. It will be compressive stress. So in compressive stress, what happens when the body is under compression and the stresses produced are compressive stress? The length of this body, for example, I have length L here, right, and after applying the forces, compressive forces, let's say that it is decreasing. So this here will become my new length L1. So this will be my compressive stress, and in compressive stress the length of the material decreases. Next I have shear stresses. Now the concept of shear force was already covered, and it's similar here. What happens is this, let's see, there are two plates here. Plate number 1, right? Here I have plate number 1, and this one here is plate number 2. Now these two plates are joined together with the help of a rivet here, right? With the help of a rivet. And if I pull this body number 1 in this direction P, I'm pulling it in this direction, and the second body here P, I'm pulling it in this direction here P, and the force so applied will be a shear force, and the stress that will be producing in this plane here. It will be producing in this plane, and it will shear this bolt here, the connection that is keeping these two plates together. The plane of shear will be generated in this place where they are being kept together with the help of this rivet. So the stress produced in this case will be shear stress. It will be because of shear stress. And what are these members? These bolts and rivets are shearing member, right? So if I read this here, when equal and opposite force acts tangentially on a body across the resisting section, then the body tends to shear off or slide across each other, right? So sliding, I'm applying a force in two different directions on these two plates, and it will slide away from each other, and when it slides away from each other, a shear stress will be developed in this body, and this shear stress here is denoted with the help of tau. This here is known as tau, or with the help of Q. So here it is denoted by tau or Q, and its SI unit is equal to Newton per mm square. So here we have, for that same body, shear stress is equals to shear force by the area of shear. So my shear force here is P and area is A. Now area where it is sliding will depend upon what kind of area it is sliding upon. Now I have a rivet here, right? Rivet. I have a rivet here. Now the area of this rivet will be equal to pi by 4 d square. So it is the area of a circle here, right? So d where pi by 4 d square will be the area of the rivet, where the area where it is shearing, right? So d here will be the dia of this rivet, dia of this rivet, d. Next we have punching shear. In punching shear, it is again the same concept. In punching shear, we'll have some plate of thickness T. This is a plate here, and its thickness of this plate is equals to T. Okay, it can be any thickness. So in general, I'm just saying its thickness will be T. Now, initially there is no hole in this plate here. Now I want to make a hole here. So if I have to make a hole here, I have to punch in in order to make a hole. So when I'm punching in this section here, all these directions that you see, pointers, will be acting as a shear force. Shear force, the force that I applied to make the hole, right? So a stress produced in this area, the stress produced in this area while I'm trying to make a hole in this plate will be equal to pi force by its area, the force that is applied and the area of this hole. Okay, and which will be, area of this hole will be equal to pi d into t. D here is diameter, t here is the thickness of the plate. So I hope this is clear again. Next we have bending stress. So in bending stress, what happens, let us say I have a column. The first thing, I have a column, right? And when an eccentric load, how does the eccentric load act? This is my line of action, or the axial point, and okay, and my eccentric force will act away from this axis, right? So this is the eccentric distance, and my force is acting here. Now this is how the eccentric force acts. And in a column, when an eccentric force acts, then the stress produced because of this force here, the stress produced because of this force, this eccentric force will be called as a bending stress. The stress so produced will be called as bending stress in case of a column. Now in case of a beam, I have a beam, and when the load acts on a transverse section, okay? So the load that is acting on the transverse section, the resistance offered by the internal beam to the bending is called as bending stress. So let us say load is acting somewhere here, right? And this will cause bending in the beam. And when the load is applied, this beam will be resisting upward. The load that is coming from upward, that load that is coming downward, the applied force, the material of this beam will try to resist, and it will push it upward, right? So this was inertia, right? And when the stresses is developed, when it is trying to resist this force, when it is developed, that internal stress is known as a bending stress. Bending stress in case of this beam. I hope it is clear again. Now strain. What is strain? Let us say I have a member here, and I'm applying a tensile force P. And now this body is under tension. When the body is under tension, its length tends to elongate, right? Let us say it has elongated this much. Its original length was equal to L. Now it has elongated after applying the force, and its length has become L1. So my strain here will be equal to change in its length, which is L1. L1, there is change in its length after applying the force P, divided by its original length is known as strain. Change in length divided by its original length is known as strain, and this strain has no unit. How it will have no unit? L1 will also be, let us say it is in meter, and L1 will be in meter. Let us say this is original length of this is 1 meter, and after expanding, let us say it has become 1.5 meter. Now I have 1 meter. The change in length here is 1.5 meter, and my original length was 1 meter. Now this same unit will get cancelled and it becomes unitless. So hence this strain will have no unit. Now types of strain. Strain, they are classified according to the application of load and mode of deformation. So these types of strain, we have linear strain, longitudinal strain, lateral strain, volumetric strain, and shear strain. Now let us look one by one. If we talk about linear strain, the first one, linear strain, when the body of elastic material is subjected to load, elastic body, let us take the example of a rubber only. I have a rubber, and this rubber, I'm pulling it this side and I'm pulling it this side. Now it is subjected to some load, right? Then there is change in its length in the direction of applied force. Now it will change, right? It will elongate. This rubber will elongate, right? Now how is it elongating? It is elongating to this direction only where I'm applying the force. It is elongating in this direction only. So this change in this length in the direction of applied force will be the lateral strain. So it will be signified as E. E is signified as lateral strain. E will be equal to change in length. This length after we apply the force, and after its length changes, that will be change in length divided by its original length. So this is the lateral strain. And the material that we generally, it can be box also. If I say I have a box and I'm just applying a force in this direction, right? And when I'm applying force in this direction, there will be change in this length, right? So this is my original length, L, and this is my change in length. Now same here, linear strain will be equal to change in length by its original length. So this linear strain generally acts along the direction of applied force. So I am applying force in this direction, so it will act along. The change in length in the direction of applied force is the linear strain. Next we have lateral strain. To understand lateral strain, let me draw a box here. I have a box, right? Now I'm applying force in this direction. Right? And what happens when I'm applying force in this direction? This length, this is the original length L. This is the original length L. I'm pulling it this side, right? So when I'm pulling it this side, it will, this length will elongate in the direction of applied force. This L, it will become this much, right? After I apply the force, let this be del L. Now, when this is changing in this dimension here, what happens? There will be this side, which is my, let this be my B, and this be the thickness of this member, right? Now, if this is increasing in this direction after applying the force, this width and this thickness will decrease, right? This side it is increasing. See the example of this one. Or yeah, I'll take this one only. Now you have to imagine it. I am applying a force in this direction. I'm pulling it. And now when I'm pulling it, the length of this pane will, the length of this pane will increase, right? But when its length is increasing, its diameter here, this will become thinner. It will become thinner as its length is increasing. So that is the lateral strain produced here. When the length of this pane increases, the change in length here will be signified as linear strain, right? But when its diameter decreases here, right, that is the lateral strain. So lateral strain here is change in lateral dimension. So this lateral dimension are B or T, width of the member and thickness of the member divided by its original, change in B or change in T divided by B or its original thickness T. I hope it is clear. Lateral strains are also known as secondary strain because it acts at a secondary dimensions. Its primary dimension here, let it be L, its original length L. I have a length L here. Length L, right? And here, let us say there will be thickness, and to the other side it's width. So this L here is the primary length, and the change in this length is known as lateral strain, and the change in its thickness, these are its secondary lateral dimensions, and change in these dimensions are known as lateral strain. So let me further explain you with the help of this diagram here. So in this diagram, the force is applied outward, and this whole body is under tension, right? And now I'm applying force, and the length of this box will change along the axis or along the direction of the applied force. So let this change in this length be del L. Its original length is L. Now my linear strain E will be equal to change in length by its original length. Now when this box is elongating, when this box is becoming flatter, it will become flatter. As it is becoming flatter, this thickness here, this thickness and this B width will decrease, and this B and this T are lateral dimensions. So my lateral strain will be equal to change in its thickness by its original, change in its width by its original width, or change in its thickness by its original thickness. So this will be my lateral strain, and here this is my linear strain. And now the lateral strain here, the lateral dimensions are its thickness, its width and its thickness T. So this lateral strain will be equal to change in its width divided by its original width, or change in its thickness by its original thickness. And if in case of a diameter, if there is a circular bar, circular bar, its dimension will be reducing, and this dimension will, I have a circular bar, right? Now I'm applying force in both the direction, and my original length initially is L. Now after applying the force, let us say that this has, the length of this bar, circular bar has increased, and it has become del L, right? So this del L by L is my linear strain, and now this diameter, the diameter of this circular bar D will also change. Originally it was D, and after applying the force, it will become lesser, it will change, right? So that small d which becomes smaller will be change in diameter d, and it will be equal to lateral strain, hence will be equal to change in its diameter divided by its original diameter. Now this diameter here, in this case of this cylindrical section or the circular bar, here is the lateral dimension or the secondary dimension. Now volumetric strain. Volumetric strain is signified with an symbol EV, and when any material or any elastic material is subjected to any kind of forces, then there will be change in its volume. Okay, if there is change in its volume, the change in its volume divided by its original volume is known as a volumetric strain. To explain shear strain, let us take the example of this diagram here. Diagram A, which is shear stress here. So let us say that this box, it's already named here P, Q, R and S, right? And at the base PQ, it is already fixed. It is fixed, right? And at the top, it is free. S and R, it is free. And you can see that at the fixed point at the base, force is applied P. Force P is applied. And again at the free end, S and R, a force is applied. So one force is pulling this area to this direction, and another force is pulling it to the right hand side direction. Now since it is fixed at the base here, this position will not move. It will not move. It will not have any effect because of this force here, because it is fixed here. But at the top it is free and it is not fixed, so hence this will move. It will move, and it will move from S, the original, its original point it was S. After moving, it will become, this S will become S1, and this will become, further it will move here, and this will become R1. So which is shown here, right? It has moved after applying the force here. It is applied in this direction, and this whole body has moved. Now you can see that when this body has moved from its original position, an angle will be formed, and this will be equal to, will be taken as tan theta. Tan theta will be equal to R1 change, there is a change in this length here, R1 divided by its RQ, this length. Okay, so but since this theta here is very small, we neglect the theta, and the shear strain produced in this member will be equal to R1 by RQ. It will be this much. Now concept of elasticity, again it's the same thing that we have covered previously. The material will remain in elastic condition only up to certain limit. Let us take the example of a rubber again. Rubber, I'm applying a force, right? When I apply force up to a certain limit, this rubber will not break. But if I apply more force, then this rubber will break, right? So there is a elastic limit even for the elastic material up to which it can take a force. If we keep on increasing the force, then it will cross that limit. It will cross the elastic limit, and the material will completely lose its elastic property, right? So that is concept of elasticity. Now Hooke's law, it is very common, this one. It states that when elastic material is loaded within its elastic limit, then stress produced is directly proportional to strain. It is again talking about an elastic material. Elastic material is loaded, it is loaded, okay, or applied force. When we apply force, that means it is loaded within its elastic limit. When we are applying this force, it is still within its elastic limit. It has not broken yet. So the stress produced, now when I am applying the force here, the stress will be equal to force by area, and the stress produced in this elastic material will be directly proportional to its strain. So this stress will be directly proportional to its strain, which means strain here is change in length by its original length, right? So my original length was L here, right? And this is my change in length after applying the force. So this stress that is produced will be directly proportional to its strain here. So this is given in here. Stress will be directly proportional to its strain. It is just for a elastic material. Now next we have modulus of elasticity or Young's modulus, and this elasticity Young's modulus is denoted with symbol E. It is denoted with symbol E, and this is again for a elastic limit. Within an elastic limit, the ratio of this stress, the ratio of stress to strain is a constant. It remains constant, and this constant is known as Young's modulus E. Okay, it is also again talking about within elastic limit. Within elastic limit, the ratio of stress by strain will remain constant, and this constant is known as our modulus of elasticity E. I hope this is clear. Next we have modulus of rigidity. Again, this modulus of rigidity is signified with symbol C, G or C or even N, and the most commonly used will be G, modulus of rigidity. Okay, and it is the ratio of shear stress divided by its shear strain. The ratio of shear stress to strain is known as the modulus of rigidity. It is simple, just the definition. Now, complementary shear stress. If we talk about complementary shear stress here, see, we have a block here, right? It is named as A, B, C, and D. Now, you see that there is a clockwise couple and anti-clockwise couple. This clockwise couple are these couples. These are going in a direction of a clock, right? So these are my clockwise couple, and my anti-clockwise couple are these couples which are going opposite to the direction of the clock. Now, to keep this block in an equilibrium, the clockwise moment of this block should be equal to anti-clockwise moment of this block, right? So this clockwise couple should be equal to anti-clockwise couple. So my clockwise couple, I have P, the applied force P into the direction. The force is applied here P, and it is going in the direction BC, right? So I have P applied force and in the direction, clockwise direction BC, right? BC. Now next, in anti-clockwise direction, it will go upward like this, right? So in anti-clockwise direction, I have applied force P dash, and it is going in a direction, in this direction BA. So I have P into BA. Now further, this P is equal to Q into AB from this diagram. So my P will become Q into AB, and this direction will remain same. BC will be equal to, again, my P dash is equal to Q dash into BC. So I have Q dash into BC, and this direction will remain same, BA. Now, since these are couples that are cancelling each other, they are in, one is going in clockwise and another one is going anti-clockwise, so they cancel each other and hence keep this block into equilibrium. So hence, cancelling these two directions, I get Q into Q dash. Here it is mentioned here, shear stress Q acting along AB and CD. AB and CD is equal to simple shear, which means the stresses that is going clockwise direction is simple shear, and the shear stress acting along AD and CB, which is anti-clockwise direction. Anti-clockwise direction, these are known as complementary shear stress. I hope this is also clear. Now we have next, state of simple shear. When the simple shear and the complementary shear acts together to keep the body in equilibrium, then it is called as state of simple shear, right? Simple shear and complementary shear, how was it working? Simple shear was working clockwise direction, simple shear, and my complementary shear was acting anti-clockwise direction, complementary shear. Now these two are acting, one is acting clockwise, another one is acting in anti-clockwise, and hence keeping this body under equilibrium. And this state is known as state of simple shear. Now next, I have a stress strain curve for a ductile material here. So it is a ductile material here, okay? So here in this y direction there is stress, and in x direction strain, right? Strain E, and here stress sigma, right? Now when a force is applied, up till this green portion here, it will remain under elastic limit, which means that if you apply force till here, till this green portion, and if you remove the force, that means it will regain back its original shape. But if you keep on applying the force, it will reach a yield strength. Yield strength, it is that point where the strain goes on increasing. This strain, it will keep on increasing. Strain will keep on increasing, and the further without much increase in its stress will not increase much here at this point. Strain will keep on increasing, stress will not increase, and at this point, is known as a yield stress. And if the material is further stressed beyond this yield point, then it will reach a plastic stage. This whole blue region here is a plastic region, and it will reach a plastic region, and even if you remove the load, then it will not be able to recover its original shape and size, right? So as we keep on applying the force, the stress will also increase in the beginning in elastic region, and the strain will also increase, and up to some limit, the elastic limit, till the elastic limit is there, if we remove the force, it will be able to regain back its original shape and size. But if we keep on applying the load, then then this material will go into plastic region, and even after removing the load, it will not be able to regain back its original shape and size. Now even in plastic region, what happens? In plastic region, if we keep on applying the load, there will be an ultimate strength point will come, where the ultimate strength will be attained. So this ultimate strength, it is a point where stress attains its maximum value, known as ultimate stress. So it attains the ultimate stress here at this point, and on further increasing the load, the material will break. So this point here is a fracture point. Here is a fracture point. On further applying the load, the material will break, and it means that the material has reached its maximum ultimate stress, and then the material will have its failure. So I hope this is clear. In the next slide, I have given all the explanation of this yield strength, plastic region, ultimate strain, fracture. So all these things are already given. So please go through it. These are the explanation of it. Ultimate strain, fracture, or breaking point. Then this diagram here shows the stress strain curve for HYSD bar. Now HYSD bar is also known as high yield strength deformed bars. Okay, form is HYSD bars. These HYSD bars have higher percentage of carbon as compared to mild steel, and their strength is higher than that of mild steel. But the yield point is not clearly mentioned. Now here the yield point is not clearly mentioned, as it was mentioned for the mild steel. So these bars and these HYSD bars are available in two types. The first one is hot rolled high yield strength bars, and the second one is cold work high yield strength bars. Okay, and this second type, which is cold worked high yield strength bars, or these are also known as torch steel bars, and they are available in two forms, that is FE415 and FE500. This cold work high yield strength bars. Okay, this is cold worked high yield strength bars, and these are also known as torch steel, or also known as tor bars, and they are available as FE415 and FE500. A twisted deformed bar has about 50% higher yield stress than the plain bars. The deformed bars has corrugation or rips on the surface of the bar. So these bars will look somewhat like this. These are its type. So these bars do not show any definite yield point. So these HYSD bars do not show any definite yield point. Okay, so the yield point is taken at 0.2% here. The yield point is taken at this point, 0.2% proof stress, which is determined from stress strain curve as shown in this figure. And the point where the line cuts the stress strain curve is taken as a yield stress, or 0.2% proof stress. Okay, so this proof stress here is a level of stress at which the material undergoes plastic deformation. That means on further applying the load, it will go into plastic zone. So till here we can say that it is still under elastic zone, and after it crosses this point here and goes to the next zone here, it will go into plastic zone. So this is the simple stress strain curve for brittle material. So brittle materials, which includes cast iron, glass, and stone, are characterized by the fact that the rupture occurs without noticeable pre-rear change in the rate of elongation. Sometimes before yielding, they fracture. So, brittle materials such as concrete or carbon fibers do not have a well-defined yield point again and do not strain harden. Therefore, the ultimate strength and breaking strength are same. So they have the same ultimate strain and they have the same breaking strength. Typical brittle materials like glass do not show any plastic deformation. So, but fail where the deformation is elastic. One of the characteristics of brittle material is that the two broken parts can be reassembled to produce the same shape and original component, as there will not be any neck deformation like in the case of ductile material. Right, and a typical stress strain curve for the brittle material will be linear. So you can see a linear line here. It will be linear, and for some materials such as concrete, tensile strength is negligible compared to the compressive strength, and it is assumed 0 for many engineering applications. Okay, at 0.2% proof stress, at this point a proof stress occurs at which the material undergoes plastic deformation again. So after applying further load, it will go into a plastic deformation. So next we have factor of safety. It is defined as maximum ratio of maximum stress here, maximum stress by its working stress. So factor of safety is equals to maximum stress by working stress. And next we have ductile material. The failure of material occurs once it reaches plastic deformation. Hence, factor of safety is based upon yield point stress. You know that for a ductile material, what happens? It goes from elastic region and further it goes, and then it will reach maximum point, ultimate strength, and it will go to fracture point, right? So this yield stress factor of safety for ductile material will be equal to yield point stress divided by its working stress, and for brittle material it will be equal to working stress divided ultimate stress divided by its working stress, which we will further do when we do the calculation. Now, percentage of elongation, how much percentage has elongated, that to find that one we have final length, which is change in length L dash divided by its original length L divided by its original length into 100 will give us percentage change in elongation of that material. So we know that what is E? E is Young's modulus E. Young's modulus E is equal to ratio of stress by strain, right? Now this stress is equal to change in this stress is equals to force by area, applied force by its area of that section divided by change in its this strain is equal to change in length by its original length, right? So from further here we get this, so it will be P by A into, now I will reciprocate it. I'll take this here is in denominator, so it will be coming in numerator when we reciprocate, so it will come this. So I want to find change in length here, so my change in length will further be equal to PL divided by A into E. So this also we'll be using in our calculation. So I hope till here it is clear. This is the end of this slide, and from the next class we'll be solving numerical on this chapter. See you in next session. Thank you.